We know that the integral of sine square over half a cycle is 1 by 2. Anyway, I have repeated this here. For a1 square integral x1 to x2, sine square is 1 minus cos twice this angle. So 2 might be there, and we have not put it's 2 twice the angle. The quantity within the bracket is nothing other than, say, this one. Dx by 2p is equal to 1. Now we will be integrating this in two different terms. Integral 1 by 2p dx minus integral, of course this constant part is there common, minus integral x1 to x2 cos twice an angle dx by 2pi. But integral of cosine over half a cycle, or from x1 to x2, will be 0, so that term will be going, and what remains is for a1 square integral x1 to x2 dx divided by 2p, that's equal to 1. Now we know that P momentum is mass times velocity dx by dt. So dx vanishes, what remains is dt divided by m, which is being put here. For a1 square integral 2 is there, 1 by 2 dt divided by m, that's equal to 1. 2m is also constant that are taken out. For a1 square by 2m, integral dt is t in the limit from x1 to x2. If it is from x1 to x2 and back, that will be completing a period, say tau. So it is from x1 to x2 only, then it is half a period, that is tau divided by 2, that's equal to 1. I have not modified any of these numbers. For a1 square, tau divided by 2m into 2, that's equal to 1. Clearly a1 square is equal to m divided by tau. 4 and 2 into 2 will be vanishing. Or a1 is equal to m omega divided by 2 pi, since the period t or tau equal to 2 pi divided by omega. 2 pi by omega is there on the denominator, so that the reciprocal will be coming to the term as omega divided by 2 pi. So a1 equal to m omega by 2 pi raised to half. So that our wave function becomes 2 by root p. Instead of a1, we have the substitution m omega by 2 pi raised to half sine of 1 by h cross integral x1 to xp dx prime plus pi by 4. That is 2 is there outside this square root. Let me take it inside. The one of the 2 will be then cancelling with that in the denominator. 2m omega divided by root p is also taken. Pi p raised to half sine of 1 by h cross integral x1 to xp dx prime plus pi by 4. This will give us a better representation for the wave function representing the harmonic oscillator, say a bound system. Now I have two corollary results to be shared with you. In the derivation of the Bohr-Sommerfeld quantization rule, we have taken two translucent boundaries as the turning points at, say, x1 and x2. Translucent in the sense that the particles are able to penetrate into the boundary or beyond the limits of the boundary. Though the probability will be falling very rapidly. See, these are represented by means of an exponentially decaying wave function. The nature of exponential decay, as you know, will be very rapid. If it is, say, having a value 10 raised to 5 at a particular point of position, in the very immediate position this will be turning to 10 power 4. In the very next immediate position this will be turning to 10 power 3. From 1 lakh to 1000, it requires an infinitesimally small thickness to be, say, penetrated. Though this is the nature, there exists a probability for finding them beyond the boundary, though it is extremely smaller. This indicates that the particle always will have a tendency to penetrate into the boundary. And such a boundary is what you call a translucent boundary rather than a rigid or an opaque boundary. See, translucency and opacity are something related with light, and we are talking about particles, and this difference is already known to you. Light also consists of particles, and in quantum mechanics we specifically talk about this kind of systems. Suppose the boundaries are not translucent, these are rigid. Both these boundaries are rigid, as in the case of, say, classical problem that we have studied, that is the case of a particle in a box problem. The Bohr-Sommerfeld quantization rule is a little different. If both the boundaries are rigid, then the equation that will help you to evaluate the energy is given by integral x1 to x2. See, here I am not taking a closed integral. Integral x1 to x2 p dx prime is equal to n pi h cross. P dx prime equal to n pi h cross. And suppose one of the wall is rigid and the other one is translucent, then you will have this equation modified as integral x1 to x2 p dx prime equal to n plus 3 by 4 pi h cross. So these results are also used or are usable under suitable experimental situations. Now we will see a case of bound system. Here also we take our classical example. Some of you might have made friendship with this fellow, that is harmonic oscillator. Even in this semester itself, you have seen the case of harmonic oscillator as a case of perturbation problem or as a case of variational method. Now in WKB also we will encounter this fellow, the case of harmonic oscillator. I am not going to represent the Hamiltonian. I am writing here only the potential energy to which the harmonic oscillator is subjected, that is half kx square, where k equal to m omega square, where with m being the mass of the oscillating system. Now to apply WKB method, of course our primary aim is to evaluate the energy eigenvalue, and the key for this evaluation is the Bohr-Sommerfeld quantization rule. As this potential is half kx square, it represents, say, two different points having the same potential symmetrically on both sides of this equilibrium positions. There can have a couplet of points having the same potential energy, as this curve is a parabolic curve. And there could be two extreme points where, say, the potential energy will be meeting the total energy, and the displacement corresponding to these points, you call them the amplitude or the maximum amplitude. If you take this as a plus a, you will have to take this as a minus a, under the assumption that the origin corresponds to the equilibrium position. So I require these two extreme points, as these points happens to be the limits of integration as long as the Bohr-Sommerfeld quantization rule is concerned. For that, I'll have to take the condition for turning point. It is the point at which the total energy meets the potential energy. That happens when half kx square or half m omega square x square is equal to total energy E. That means x square equal to 2e by m omega square, and I'll represent this constant point as, say, a, and I can have two different choices for a having the same magnitude, a equal to square root of 2e divided by m omega square. Now look at the Bohr-Sommerfeld quantization rule. I am writing it not as the closed integral from minus a to a in p dx prime equal to n plus half h, with p being root 2m into e minus v equal to n plus half h. Now integral from minus a to plus a, integral from minus a to plus, here I might have put, say, this as closed integral. See, the closed integral result is used. This is an error. A and minus a might not be here. So this is 2 times integral from minus a to a root of 2m into e minus 2m into v. Instead of v, I have put a half m omega square x square dx. The right side is retained. This is now twice integral minus a to a 2m into e. E from this expression is nothing other than half m omega square a square. So we can put e as half m omega square a square. Half vanishes, m becomes m into m square omega square a square, minus 2 vanishes, m square omega square x square dx equals n plus half h. Now twice integral minus a to a. Integral from minus a to a can be written as, say, 2 times integral from 0 to a in magnitude. So that 2 with these 2 make it, say, 4. M omega is a common factor for this square root. M square omega square is taken out, and out of the square root we will have m omega. Integral from 0 to a, root of what remains is a square minus x square dx equals n plus half h. That is for m omega. Either you can put x equal to a sin theta here. X can be put as, say, a sin theta, x equal to a sin theta. The limits of the integration then needed to be changed. When x is equal to 0, sin theta is equal to 0. That means theta equal to 0. When x equal to a sin theta equal to a vanishes, sin theta equal to 1, theta is then pi by 2. And you can put this as, say, a square into 1 minus sin square theta, that is a cos theta, and can be integrated. But I recall this result, integral from integral root a square minus x square is a square by 2 sin inverse x by a. So let me use that flexibility. I have evaluated this integral a square by 2 sin inverse x by a in the limit 0 to a equal to n plus half h. For m omega by 2 a square. See, look at this expression. A square is nothing other than 2e by m omega square. So it is written here 2e by m omega square, because I am interested in evaluating the energy eigenvalue. So on the left side, I will have to obtain somehow, say, energy E into sin inverse x by a. Upon giving upper limit, say, sin inverse a by a, sin inverse 1, that is pi by 2, minus sin inverse 0, which is 0. That's equal to n plus half h. Now 2 into 2 vanish with this 4. M omega vanish with this m and omega square. Take 2 pi to the right side. E is retained on the left side. Take omega to the right side to make the expression for energy or the evaluated energy as E is equal to n plus half h divided by this 2 pi is here. H by 2 pi is written as h cross. Omega is taken to the right side, say, to make the expression for energy, general expression for the energy of the nth quantum state of linear harmonic oscillator as n plus half h cross omega. This also gives us the 0 point energy corresponding to n equal to 0 as, say, half h cross omega. So WKB could be effectively applied in the case of the linear harmonic oscillator problem, and we have obtained the result that is purely a quantum mechanical result, though we have seen it several times. With that, let me conclude our discussion on bound state. A few assignments for you. I have some corollary results. Assignment 1. You prove those corollary results. You can refer Applications of Quantum Mechanics by Nuruddin Zetali. Now assignment number 2. Apply WKB method to evaluate the energy of particle in a box problem. Assignment number 3. Do the same for hydrogen atom problem. These are important. You can have a problem question for your examination coming from this Bohr-Sommerfeld quantization rule. All these problems are discussed in the standard textbooks. You can refer those textbooks as well and try to timely submit your assignments